Hello everybody, my name is Gonzalo Alvarez and I am here to present a paper for the 2020 International Conference on Decision Aid Science and Application, and the title of the paper is Enhancing of the Operational Decisions in Electric Power System under Blackout. Authors are Gonzalo Alvarez and Maria Julia Blas. All sectors of society are affected by the power outage. A blackout causes traffic paralysis in the cities, interruptions on telecommunications, stops in industries, issues in government sector, problems in hospitals, the impossibility of pumping in drinking water treatment plants, problems in electric transport, among other issues. In many regions of the world, the expansion of the electric power systems was not conducted in an organized manner. They only responded to the most urgent needs of the moment. This gave rise to electrical system with a high degree of instability, which is very prone to generate failures, outage, or even blackouts. The causes of these failures in the systems, along with the possible blackouts they might cause, are several. Among them, there may be overloading of the lines, increased demands, lack of maintenance, maneuvering problems, or weather problems. Blackouts may experience different degrees of severity and duration. Every day, many of them occur around the world, and the vast majority has a short duration and low level of affectation. However, in recent years, there have been blackouts that have represented a great impact and relevance by the number of users affected and the economic loss. In 2003, a blackout occurred in the US and Canada, causing a power loss of about 62 gigawatts over 2 days, and direct economic losses about $6.4 billion. In 2012, the combination of 3 blackouts in India caused the largest recognized one in history, leaving more than 600 million users without service. More recently, during 2019, a failure in the Argentine electricity system causes the blackout that affects the whole country, along with part of 4 neighboring ones: Uruguay, Chile, Brazil, and Paraguay. The study of these outages is important to enhance the operational decisions and prevent repetition of these events in the future. There are several works in the literature that present different techniques to improve the operations, avoiding blackouts. In consequence, this work presents a mathematical model that provides the following main contributions. The model studies the operation of a large-scale system, helping to make decisions about its performance and security. It analyzes the propensity of the system for developing lines failure by introducing 2 new factors. This allows for obtaining less risky operation schedules. In case of failure, the model can obtain feasible solutions that allow the redispatching of load. In this way, the operation of the system can be reorganized to continue working, leaving the less possible number of users without service. The calculation proposal can be performed before the operation time. It means a pre-dispatch model, or after that incident occurs. For the first instance, the method could offer alternatives for the operational decisions in order to avoid the blackout. And for the second instance, the method becomes a powerful tool to analyze the reasons that causes the blackout, and it can elaborate corrective actions to prevent blackouts in the future. The proposed model is applied to a real case, the blackout in Argentina in 2019. The causes that led to this collapse will be analyzed and possible solutions will be provided. For this purpose, the consult data is reported by official agencies. The new model allows simulating the state of the lines and to analyze their situation. It also allows studying how far the system can be kept operable in case of a failure in the lines. The new objective functions is presented in the Formula 1. The first term is the sum of generating cost. It is composed by different sources, which are thermal with natural gas, thermal with liquid fuels, hydropower source, photovoltaic, nuclear, wind, and other renewables. Second term represents the power transactions between neighboring systems. And the third term establishes the impact of the risk of outage in each line, where F sub LT is the power flow in the line L at time t. Sigma carry status is the factor that indicates the overlap degree of line. Sigma carried risk is the risk factor of line L. Depending on the predisposition of the line to suffer some kind of outage. This factor must be provided by the independent system operator, according to the information available. The value should be close to 0 when there are no report dangerous conditions for the line, and it is close to 1 when there are dangerous conditions, such as storms, racing drivers, lack of maintenance, among others. Besides, raw carried line is the cost of transmitting electricity on a line that might collapse. After that, the state of the lines are analyzed with the factor sigma carried status following the Formula 2. The average between the two factors, sigma carried status and sigma carried risk, must be less than 0.7, otherwise the line may collapse. If the average exceeds the mentioned value, the redispatch model is calculated. The test case is the blackout of the Argentine Interconnected System, or SADI for its acronyms in Spanish, produced in 2019. The analyzed data is contained in the report presented by the Secretariat of Energy of Argentine Republic. This event occurred on 16th of June. The Argentine system supplies electricity to more than 40 million people. Besides, it also handles electricity transactions with its neighboring countries, Uruguay, Brazil, Chile, and Paraguay. This system has more than 100 generating companies, one company that transmits high voltage, and 74 distribution companies. The composition of the system, with its 9 regions and the 500 kV transmission system, is shown on the map on the left side of figure 1. Test cases are solved by using the software GAMS. Before to discuss the results, it is important to present a brief review of the blackout. At 7:06 a.m. that day, the demand of the study was 13,200 megawatts. In the morning that day, there was thunderstorm activity in the area where the short circuit is going to be produced. As a result, the probability of network failure is high. However, the independent system operator decides to continue transmitting in the same way. As for the configuration of the transmission network, Transenergy, the company in charge of the high voltage transmission, had built a temporary connection or bypass between Colonia Elía Campana and Colonia Elía Belgrano lines. It was due to maintenance tasks. Exactly at 7 hours 6 minutes 22 seconds, a short circuit was produced on the Colonia Elía Belgrano line, the rest of the bypass. The figure shows the detail of the lines with the short circuit. As a result, the automatic generation disconnect did not work. Consequently, a large part of the system was isolated. Besides, the action of the under-frequency load break relays was not performed correctly. In addition to these situations, several generators were disconnected from the network before the minimum established time when the frequency drops. All this action produced the great blackout, and it took more than 14 hours to restore the whole system. The new model analyzes the situation before the moment of the incident. As can be seen in the left figure, the lines with values of sigma carried status higher than 0.7 are marked in red, while the lower values are shown in green. Besides, the figure on the right side shows the weather forecast for the whole system. It corresponds to the day of the blackout. It can be seen that in the region where the incident took place, there is a forecast of thunderstorm. Because of this, the factor sigma carried risk for lines number 3, 7, 4, and 6 will be equivalent to 1. Taking into account the definition of both factors, the average between them takes the greater values to lines 6, 4, 1, and 2. In consequence, the alternative load dispatch solution is calculated by applying the new model. As a result, the cost of the alternative solution constitutes an increase of only 0.05% over the original solution. When the power flows of dangerous lines are analyzed, it can be observed that the alternative solution reduces the values for line 4. And similar situation occurs with the values of the line 6. We conclude that the new mathematical model allows analyzing the operation of a large electrical system considering the potential risk of its elements. In this case, the model analyzes the degree of the propensity of a line to failure. In case the model registers a high degree for one of these lines, a flow redispatching calculation is produced. The goal is to reduce the power flow transported by these lines, and even if the outage occurs, the impact on the system is reduced. To test the model, a real case is studied, the great blackout of the Argentine system on 2019. In this case, the model previously recognized the high risk level of the line that failed. The model proposed an alternative option of redispatching the flows that circulate through the mentioned line. The model can be also applied at the pre-dispatching scheduling. As can be observed in the results, the model indicates that the zone where the short circuit was going to happen presents a high risk level. This is where the work finds its better application. With this explanation, we conclude the presentation of the work. Thank you very much for your attention.